Coulomb's law quantifies the electric force between two point charges. Discovered in 1785 by Charles Augustin de Coulomb using a torsion balance, it laid the foundation for electrostatics. This force is non-contact, meaning it acts at a distance, and is central to the study of electric fields and interactions between particles in physics and chemistry. The formula for Coulomb's law is F equals K times Q1 times Q2 divided by R2. This inverse square law means force increases rapidly as charges get closer. F is force in newtons, Q1 and Q2 is charges in coulombs, R is distance in meters, K is Coulomb's constant. The force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. There are two types of electric charges, positive and negative. Like charges repel and unlike charges attract. This behavior results from the electromagnetic force, one of the four fundamental forces of nature. Charges are quantized in units of elementary charge. Electric force is a vector quantity, so it has both magnitude and direction. Direction depends on the signs of the interacting charges. Using free body diagrams helps analyze the net force on a charge when multiple charges are involved. Gravitational force is always attractive. It acts on mass and is very weak. It is also important for planets, stars, and galaxies. Electric force can attract or repel. It acts on charges and is much stronger than gravity. It is important at atomic and molecular levels. Both forces follow the inverse square law, and electric force dominates at small scales while gravity dominates at larger scales. Electric forces are 10 to 39 times stronger than gravitational forces for subatomic particles. This explains why atoms hold together despite the tiny gravitational pull, and it also explains the structure of atoms, molecules, and matter as a whole. An electric field is a region around a charge where a force is felt by another charge, and the equation is E equals F divided by Q. Field lines point away from positive and toward negative charges. Electric fields allow us to predict forces without direct contact, and their direction and density represent the magnitude and direction of the field. Fields obey the superposition principle, so the net electric field at a point is the vector sum of fields from all sources. This principle is essential in analyzing systems with multiple charges, such as dipoles or complex charge configurations. A real-life application is static electricity. Static electricity occurs when electrons are transferred through friction. So an example is rubbing a balloon on hair, and the resulting charge imbalance causes electrostatic attraction or repulsion, which is explained by Coulomb's law, and this is also why clothes cling together in a dryer. So this is a real-life example, and if these were the numbers for each, and you did the math correctly using the formula F equals K times Q1 times Q2 divided by R2, you get F is around 0.216 newtons. This shows how to use the formula to predict the electrostatic force between charged objects, reinforcing the quantitative power of Coulomb's law, and shows how to predict real forces between charged particles.